Good morning, ninth grade. Hope you guys are doing well. We are going to get into electricity's closely related cousin, and that is magnetism, as you can see here. Let's get it started. Now, magnetism is very important when it comes to electricity because they seem to both behave very similarly as well. A lot of the times when I talked about electricity, you guys noticed that I used a comparison with magnets. And so magnetism and electricity are brought together a lot. In fact, we talked about and showed electromagnetism in class a couple times here. So let's just talk about magnetism by itself. Now, what I have here is a very interesting rock. And it is a naturally found stone that attracts metal objects. Now, medieval Vikings knew about these and they used them. They were called lodestones. And I spelt that wrong, but oh well. Anyway, so to point them toward north. Because lodestones were attracted to iron, they were called waystones as well. And so what would happen is they would take those lodestones, like that guy has in his fingers right there, and they'd put it in a bucket of water, and it would float. And then it would constantly go toward north on its basically by itself, and so they thought it was a magical stone that was able to tell them which way north was, calling them lodestones, and lodestones are natural magnets, and so you don't need to do anything like put electricity in them like we watched in the video in class about putting electricity through the nail to get electromagnetism. You don't have to do that to charge up a lodestone. They are just naturally magnetized right there. Now magnets are known as objects capable of attracting objects capable of attracting other objects by magnetic force or magnetism. So, this whole chapter is going to be on using magnets and things like that. The nature of magnets. Now, this picture to the right here, you can actually see different objects that you may have in your home that use magnets. Now, we have the compass, we have speakers, some headphones, what looks to be a scale here, a TV, and even this refrigerator all use magnets in some way, shape, or form in order to perform what they're supposed to do. Now magnets can be found in all these things here, including even generators and motors of different types. The Tesla, for example, has a magnetic motor that helps it to work the way it does. Now, electrons act like small magnets, and planets, such as Earth, are large magnets. And so, if you guys have never heard this before, I'm telling you right now, Earth is a giant magnet. Now, it's not as strong on the surface as it is at the core and places like that, but it is still a strong enough magnet to attract things to it, slightly. It's not as strong as a magnet you'd hold in your hand. It doesn't give as much of the same effect, but it is still a strong magnet. Now, even though magnets come in many shapes and sizes, they do share some similarities. And so these similarities are what we call the laws of magnetism, and we're going to get into some of them right now. So now, the first one is the law of magnetic poles. This one comes with a little bit of history here. It says, in the 13th century, Pierre Le Pèlerin de Maricourt wrote a letter describing different properties of magnetism. And so this was the first guy to really get into magnets and start really working on them. And he says here, he discovered that the magnetism in a lodestone is concentrated at the two poles, a north pole and a south pole. Now the north pole is called the way it is because it will actually point towards the north, and the south pole was called the way it was because it would point towards the south. Now you can see this magnet here has a south pole here and a north pole here, and they're attracted. The north pole is attracted to the south pole of the earth, and the south pole here is attracted to the north pole of the earth. This is because the law of magnetic poles here, and it says magnetic poles always exist. If you cut a magnet in half, they will develop a new pole where you cut it. And so that is an interesting fact to know as well. But when I was talking about the other slide, it goes to this here. The like ends of magnets repel each other. North repels north and south repels south. So if you were to take some magnets that you have lying around right now, you would notice You try to push the two sides that repel next to each other. They're both like poles. And sometimes when you're pushing them close enough, they'll actually flip around and then stick together. And that's because it's trying to get to the side where it actually is attracted to the other magnet and then stay locked on. And so that has to do with this idea here. The different or the opposite poles on a magnet attract each other. And the like poles repel each other and push each other away at a very, very, very strong power. Now, you can actually see magnetic fields by doing this experiment. If at home you guys have some iron filings and you have a bar magnet, you can actually put the bar magnet on a piece of paper and then sprinkle some iron filings on top of it, and it will form these lines, and that will show us the magnetic field around the magnet. And you can see here, let me just get my laser pointer out, that near the two poles of the object is where the most iron filings are, and that's because those are the strongest parts. Now, the regions surrounding a magnet in which other objects are affected by its magnetism is called the magnetic field. And so the magnetic field is strongest at the poles, here and here, and weakest in the middle. And so there isn't a lot of attraction. There aren't a lot of iron filings on the magnet around here. But there's a ton at the two poles here. And so you can actually see it makes these really cool line patterns. We have a name for those. It says when you put iron filings on around a magnet, you can view the lines of flux. And so these are basic lines how the magnetism works around the magnet. And they form and they look really cool. And it basically shows you the magnetic field in real life, which is difficult to see because the magnetic field is usually invisible. So using iron filings or iron powder, you can actually look at it and see it for yourself. Now from here, we go into our last slide of the day, which is the law of magnetic force. Now this was created by Charles de Coulomb, and it was to describe the force between two magnetic poles. Now, let's look and see how this works. So we have Fe, which is the force. We have Ke, which is Coulomb's constant. And you have this number here that's going to show up every time you use this, which is 8.987 times 10 to the 9th power. Then you have Q1 is one pole of a magnet. Q2 is another pole of another magnet. And then R is the distance between the two charges. Now, one thing to notice here is when you have an equation set up like this, the bigger the number R is, and so the further away the two magnets are, the less magnetic force there really is. The closer together the two magnets are, or the lower this R is, you'll see that it is actually making the magnetic force larger. Alright guys, well, sounds like I have something I have to attend to. Hope you guys have a wonderful day, and I will actually give you guys some questions on Google Classroom. I will see you tomorrow. Goodbye.